Welcome. Today's topic is the derivation of the equation of an ellipse from its definition. So, what is given? Given are two symmetric points on the x-axis. So symmetric with respect to the y-axis, and we say it is minus f 0 and f2 is then plus f 0. We sketch these 2 points here in the xy coordinate system. So the f1 point is here and the f2 point is here. So f1 is a focus and also f2 is a focus. Or the plural, they are two foci. So, and here the distance between the origin and f1 is my small f given by the point. So you can also say the f is given. So the ellipse now is defined as the set of all points for which the sum of the distances to the two fixed points called foci f1 and f2 is constant. Let's probably start here, for instance. So this point, and if you connect these two, this and this, they both have, let's also say, a given length a. So also the a length has to be given here. And people then also say that this is length b. So the distance between f1 and f2 to these fixed points from this point is constant. And now you move it along. So this means here, if we are here, we are there and here. And from these 2 points here outside, it is also here a. Let's use the red color again. So here it is a, and also to that one it is also a. If you, for example, consider this left point, you have here to foci f2, to focus f2, you have a plus f distance, a plus f, and to focus f1, you have a minus f. So a plus f plus a minus f is again constant to a. So this is fine. And if you now want to figure out what is the profile, so probably another point P, depending on xy, is here. And now you can plot the ellipse. Fine. So now we are interested in deriving an equation. So first, what we have studied in this sketch here, we write it down mathematically. So the ellipse are all the points x, y, where the distance from focus f1 to the point P is plus the distance from the point f2, focus f2 to the point P is constant. And in our case, we said it's 2a. We have chosen 2a. And this equation fulfills all the xy points of this graph here to match this black ellipse. Yes, what is a simple equation for this ellipse? So we go on. You know the rule here, tip minus shaft. So it's P minus focus F1. The P point is XY. And the first focus has coordinate minus F. So minus F is plus F. And the other coordinate is 0. Plus, again, tip minus shaft, P minus focus F2. So we have XY. And now we subtract the F as there is no minus. And this should be equal to A. So what is the magnitude? It's the square root of the components squared. And now you have to solve this root equation. And this is actually not so simple. So I will first, because I want to avoid two roots on one side, I first move this to the right side. So I rewrite it again, and then we are able to square. So again, a lot to write here. And now we square both sides. And I already write down the expression inside fully expanded by using the binomial formula. So x squared plus 2xf plus f squared plus y squared is equal. Here I have to use binomial formula outside. 4a squared minus double product. Then this root expression. And what remains is this inside without the root, because I square it, but I also write it down fully expanded. So we have x squared minus 2xf plus f squared and my plus y squared. So with this type of equations involving roots, we unfortunately have to square twice because there is still a square root here. We have to square the equation again. But before you do that, you have to simplify it. So first, what cancels out here? Canceling out is fortunately the x squared. Then the f squared cancels out. And also the y squared is cancelling out. And what remains is just, if you shift the 4a root expression to the left side, so it is 4a square root the root expression, and this should be equal 4a squared from above and minus 4xf. If you put this to the right side, and now you see there is the number 4 which is cancelling out, and square it again to get rid of the square root. So it is then a squared times opening brackets and also fully expand inside already, x squared minus 2xf plus f squared plus y squared. And on the right side you have to use binomial formula, a to the power of 4 minus 2a squared xf plus x squared f squared. Again, you see expressions which simplify. So minus 2x fa squared is also on the right side, cancelling out. Next, we factor out the x squared here. And what remains on the left side, if you factor out x squared, is a squared. But there is no x squared here on the left side anymore, so I look to the right side. If I factor out x squared, what is then here is minus f squared. So I have combined this and that. Yeah. What remains still here is plus a squared y squared from here. Yeah. And on the right side, I factor out a squared also. So what remains is a squared inside and minus f squared. I think that's not too fast. Hopefully you can follow. So it's this part, and from the left side minus a squared f squared. Okay, Now go back to the sketch. What can you see here in the sketch by the Pythagorean theorem? That b squared is a squared minus f squared. A squared hypotenuse minus f squared is b squared. And now I can use this here. What is a squared minus f squared in this case? It is b squared. And the same on the right side. A squared minus f squared is also b squared here. And now we arrive at the classical formulation of an ellipse. I continue here on the left side. So I multiply the whole equation by 1 over a squared b squared. So I divide by a squared and b squared. And here is it. X squared divided by a squared plus y squared divided by b squared. I hope you can see it here. So x squared, b squared's cancelling out. So a squared in the denominator remains a squared y squared divided by a squared b squared. A squared cancelling out, what remains is b squared. And on the right side, you have a squared b squared. It is equal to 1. So the most simple available representation. And these variables, a and b, they have special names. They are called semi-axes. And you see here the a is the intersection with the x. Here in this case, minus a plus a. And the b, or minus b here, are the intersections, the intercepts with the y-axis. So before I continue here, let's write it here once again. So a and b are the semi-axes. I want to discuss a special case, which is also very obvious. What if the semi-axis a and b are equal to the radius r, so they are the same? Then what about this ellipse equation? So x squared divided by r squared plus y squared divided by r squared is equal 1. And this actually then can be reformulated as the circle equation. X squared plus y squared is equal the radius squared. So the circle is a special case of the ellipse. So there is also another representation of the ellipse, a so-called parametric representation. And probably I have enough space to discuss it here in this region. This is also straightforward. So I want a curve representation, a parametric representation for coordinate x and y depending on an additional parameter t, which can be the time, for example. So if you want to move circular, you need cosine and sine. This is for sure what we're gonna need. Cosine and sine t. But instead of radius, here we have now our semi-axis a and b. So this is different. For this parametric representation, the range of the parameter is from 0 to 2 pi. So let's look to the sketch. Where is actually t equals 0? So if t is 0, you get here cosine 0 is 1. So a sine of 0 is 0, a 0. So you're gonna start here, which is t equals 0 in our sketch. And then you go counterclockwise. So here t is equal pi half. That's the next point. then you have here t is equal pi, and on the bottom you have here t is equal 3 pi half. So if you are unsure about this, always plug in the point t equals 0. For example, x evaluated at 0 is in our case a 0. This is what I explained before, and the movement is counterclockwise. The question is, why is this describing the ellipse? Is it really fulfilling the elliptic equation? And the answer for sure is yes, otherwise it wouldn't be here. So let me remove this special case here. So we actually now prove that our parametric representation fulfills this equation of the ellipse. So you plug it in, which is a squared times cos squared t divided by a squared plus b squared sine squared t divided by b squared, and this should be equal 1. We ask, is it really equal to 1? And you see here we can simplify the a squared, we can simplify the b squared, and then we arrive at the well-known equation cos squared plus sine squared is equal 1, and this is true. So I want to conclude this video how you can remember this formula with the distances being constant like this, so that the distances are constant. Suppose you want to create an ellipse-shaped flower bed in your garden. How do you do it? You drive 2 stakes into the ground, located at the foci F1 and F2. Then you take a string that is exactly 2a long, 2 units long, whatever, meters. You stretch the string tightly, yeah, and move around, keeping the string tight so that the sum of the distances of the 2 foci is always 2a. By doing this, you trace out the shape of an ellipse-shaped flower bed. This is also called the gardener's method. I hope this helps for deeper understanding. Thanks for your attention and see you in the next video.